Good morning. Starting from this session, the next few sessions, we will be looking at the functions of the data link layer. Now the data link layer, as we all know, is the second layer in the network protocol stack, residing just above the physical layer. Now to give you an overview of what functions are there normally at the data link layer. Now what is the goal first of all of the data link layer? The goal of the data link layer is to make sense of the data. That is, you have a set of raw bits coming out of the physical layer, and to make sense of this bits that are coming out of the physical layer is something which has to be done by the data link layer. Now in order to do that, there are four functions that we normally talk about as being done by the data link layer. One is framing. Second function is flow control. Third function is referred to as error control. And the fourth is link access or media access control. What we mean by framing is that the data that has to be transferred has to be organized into some kind of a format so that the receiver is able to interpret the data appropriately. Flow control refers to the problem that we have when you have a fast sender and a slow receiver, in which case you need to control the rate at which the data flows from the sender to the receiver so that the receiver will be able to receive the data correctly. Error control is something that we have because we will have errors during transmission, and if there's an error in transmission, we should be able to detect that an error has occurred and either correct it or ask for a retransmission. So this job of detecting errors and doing whatever is necessary for that comes under error control. The fourth function we talk about is link or media access control. Now this is something which comes up whenever we have a shared media. So when you have a media which is shared by a number of nodes, then we need to determine who gets access to the channel at a given point of time. Obviously, when you have a shared media, if there are two people transmitting at the same time, it will result in collision and loss of data. So to avoid that, we need to have a mechanism to determine who will transmit at a given point of time. So that is normally handled by the media access control. So these are the four primary functions that we need to understand at the data link layer. Let us look at the position of the data link layer in the protocol stack. So as we said, the data link layer is layer 2 of the protocol stack, sitting right above the physical layer. So if you look at the internet model, you have the physical layer, then right above that we have the data link layer. If you look at the IEEE standard, so here you will see that above the physical layer, there are two different functions which are talked about. Both of this actually comprise the data link layer. You have media access control and the logical link control. So media access control, as we just mentioned, is determining who gets access to the media, and logical link control takes care of the other functions, namely flow control, error control, and so on. We could go one step further and do what is called as error correction. So what we do here is the receiver identifies that an error has occurred at a particular bit and corrects the bit error without resorting to retransmission. Without asking for a frame to be retransmitted, it is able to automatically correct for the error that has occurred. So this is error correction. Let us look at where exactly the link layer function is implemented. We'll see that the link layer function is implemented in the network adapter itself. Now remember that whenever we need to connect a device to the network, you will have a network interface card or network adapter that is used. We talk about Ethernet card, we talk about 802.11 card, and so on, right? So it is in these cards that this link layer function will be implemented. In fact, the link layer function as well as the physical layer function are normally implemented in the network interface card. So what will happen on the sender side is that the datagram which comes from the network layer will be given to the network interface card, and it is the job of the network interface card to convert that into frames and then into bits and then send it out as signals on the physical link. On the receiving side, the signals are received by the network interface card, converted into bits, and then into frames are extracted from that, and then the data is extracted from the frames and given to the network layer on the receiving side. So the functions which are done at the sender side are encapsulation of a datagram into a frame, addition of error checking bits, flow control bits, etc. On the receiving side, it first looks for errors, looks for flow control information, and so on, and then extracts the datagram and passes it to the higher layer. Going one step further into the different functions, framing refers to the encapsulation of datagram into a frame structure by the addition of headers and trailers. Now headers and trailers, the information that you have in the headers and trailers will be dependent on the flow control techniques used, the error control information that needs to be sent, and so on. Another important aspect that we have in the frame structure is the specification of physical addresses to identify the source and the destination. Now remember that we are highlighting the term physical addresses here because we want to differentiate this from the logical addresses which are used at the network layer. So when we talk about IP addresses, for instance, they are logical addresses. So here we talk about physical addresses which are given to the source and the destination machines. Physical addresses would also be referred to as MAC layer addresses or the physical addresses, which uniquely identify a particular machine. Now talking of link access, whenever we have a medium that is shared, there are different topologies in which the different devices could be connected to one another, and accordingly there are different access mechanisms which are defined. Coming to the next function of flow control, what we try to ensure using flow control is that the sender should not overwhelm the receiver. Remember, as we said earlier, flow control is a fast sender, slow receiver problem. So that needs to be handled. When we talk of error control, there are two different options available. One is error detection and the other is error correction. Now remember that errors will be caused for various reasons. It could be signal attenuation, it could be some electrical noise, it could be some external disturbances. Something could cause error. So what we need is that the receiver must be able to detect that an error has occurred. So once it detects that an error has occurred, then it could just simply drop the frame and do nothing about it, or it could signal the sender asking for the data to be retransmitted. So this is what is normally done under error detection. Now, with this overview of the different functions that we have at the data link layer, let us look at each of these things in more detail. We will start with framing. Now, the framing technique that is used varies depending on whether we have synchronous or asynchronous transmissions. First, let's understand what we mean by a synchronous or an asynchronous transmission. Now, in general, there are a number of synchronization tasks that need to be carried out. Or we say there are different levels or a hierarchy of synchronization tasks that need to be carried out when data is sent from a sender to a receiver. The first level is a bit level synchronization. That is, we need to recognize the start and end of each bit. When a series of bits are received at the receiver, it should be able to recognize where a bit begins and where a bit ends. Now this bit level synchronization is normally handled by the physical layer. The second level of synchronization that we have is at the character or byte level, which is recognition of the start and end of each character. That is, we look at a unit of data now, but a small unit of data, say a byte or a character, and we are talking about recognizing the start and end of each character or byte. That's the second level of synchronization. The third level of synchronization that we talk about is at the block or message level, where we are talking about a larger unit size, typically that of a frame, and we are talking about identifying the beginning of a frame and an end of a frame and identifying the frame within that. So of these three levels, the talk of asynchronous transmission comes only when we are talking about a byte level or a character level transmission. That is, when a character or byte is being transmitted, we need to identify the beginning and the end of each character that's being transmitted. That is, we're talking about a situation where characters are not sent continuously, but you're sending a character and you may have a gap and then send another character. So it's not a continuous set of bits that are being sent, but you can have a set of bits representing a character which are being sent, then a gap, and then a set of bits representing another character, gap, and so on. That is, this is to take care of situations where you may have some intermittent transfer of data, or some data being transmitted at some random intervals of time and so on. So remember that when we talk about asynchronous here, so it's only asynchronous at the byte level, which means that the bits are still synchronized. That is, at the bit level, for the physical layer to recognize the bits correctly, their durations of each bit, the duration of each bit would be the same, so that it's able to identify the bits appropriately. Okay, so the asynchronous, when we do asynchronous transmission, what is normally done here is, whenever a character or a byte is transmitted, so before transmitting that, you send a start bit at the beginning and one or more stop bits at the end of each byte. Now, this is typically how the bits would be sent. So for instance, let's say the line was idle, and idle line is indicated by a high level signal, and a start bit which indicates the beginning of a character of data is indicated by a low level signal. So now you can see that before the data bits are being transmitted, you first have a start bit. Now the start bit may be of a different duration than a data bit. In this case, we have used a 1.5 bit duration. You can see this is 3t by 2, where the bit durations are all t. So you can use a 1.5 bit start bit, and then that is followed by the actual data bits. So 1 to 8 are the data bits, and then we have one stop bit to indicate the end of the character. So start bit indicates the beginning of the character, and stop bit indicates the end of the character. Let us look at how a series of characters will be transmitted using this asynchronous transmission scheme. So we have the sender here and the receiver here. This is the direction of flow. So every character that is sent has a start bit at the beginning. We are assuming that we have 0 as the start bit and 1 as the stop bit. So in between we have the data. So you can see here that already some bits have gone into the receiver. So this is the stop bit of the data that's already being received. Then we have a gap here. Then the next character begins. So you have a 0 here, data bits, then the stop bit, a gap, 0 which is the start bit of the next character, data bits, stop bit, then again a gap, and then 0 which is a start bit, and then the data bits. This will be followed by the stop bit. So this is basically how the data will be sent. Now coming to synchronous transmission, the situation here is that the complete frame is transmitted as a contiguous string of bits, and the receiver endeavors to keep in synchronism with the incoming bit stream for the duration of the frame. That is for the entire frame. It's not just a single character that's being transmitted, but a group of characters which form a complete frame is transmitted as a contiguous stream of bits. Okay. So in the case of synchronous transmission, we're talking about blocks of characters transmitted without character level start and stop codes. But anyway, there has to be some kind of synchronization that has to be provided between the sender and the receiver, right? So normally there are two ways in which it could be done. One is that you could have a separate clock line that is being sent, so which will provide the synchronization. Okay, but that is a little difficult to do when you have long distance transmissions. So this idea of a separate clock line is used when you have very short transmission lines. For instance, when we talk about within a computer, when you have one card talking to another card, you have a communication between a card and another card. So in those cases, you will find that we use a separate clock line as part of the bus which is used to connect the two cards that we have. So that works in the case of short distance communication. But when we talk of a network where you're talking about one device, another device being connected to each other, this separate clock line normally does not work out. So what is done instead is that we use some kind of a coding technique where the clock information is embedded into the data. For instance, when we talk of biphase coding, which is used in at the physical layer, when we talk about different coding schemes, you will find that the coding schemes are normally done in such a way that you will be able to extract the clock information from the data that is transmitted. So that is the technique which is normally used. So given that we have some mechanism to extract the clock, and therefore the sender and the receiver can stay in sync. So in synchronous transmission, all we have to worry about is how do I identify the beginning of a block of character and the end of a block of character. So let's look at schemes which are used for that purpose. So to identify frames in synchronous transmission, what is normally done is that the frame contents are encapsulated between a pair of bit patterns, one called the preamble bit pattern and the other called the postamble bit pattern. So this bit pattern is a special bit pattern that is used to identify this is the beginning of a frame. Okay. The same thing is true about the postamble bit pattern as well. Okay. So these may be, sometimes these are some reserved characters which are used, and the purpose of using those characters is mainly to provide this frame synchronization so that you can identify the beginning of a frame and the end of the frame. So this kind of a what is called as a sentinel based. So in the sentinel based framing mechanism, we use some special characters to identify the beginning and the end of the frame. So the special character or a pattern that we are talking about, it could be a character or it could be a bit pattern. So we talk about two things. We talk about a character based framing technique or a bit oriented framing technique. So it's a character oriented framing technique. Then we have these characters which are used to identify the beginning and the end of the frame. If it's a bit oriented framing technique, then we have a special bit pattern which is used to identify the beginning and the end of the frame. So in a character oriented framing pattern, we have these special characters called STX and ETX which is used. Now this is just an example. Different protocols which we have at the data link layer use different such characters. This is one such character which is used. So you can have a STX or ETX character and a data link escape character, the DLE character also, which is used as a special character. So this is an example of a character based framing scheme. Now in bit oriented framing, what you have is that this is a particular sequence of bits which is called as the flag bit. This is normally used in the HDLC protocol. Now the only problem we have is when such a character pattern or a bit pattern appears as part of the data itself. So what will you do then? Because this data now will be interpreted as if it is a special character. So we need a mechanism to handle that. So what is the solution for this? The solution that we have for this is called as bit stuffing or character stuffing. That is, in the case of bit oriented framing, we use the technique called bit stuffing. In the case of character oriented framing, we use the technique called character stuffing. So what is bit stuffing or character stuffing? It's very similar to escaping special characters. Now this is very similar to escaping special characters that we write in C programs, right? So for instance, when you do a printf and you want to print out a slash. So what do? You normally have another slash used as an escape character to escape this special character that we are talking about. So similarly, in the case of framing also, when I need to have a special character as part of my data, I make sure that I add an escape character before that, so that the receiver will be able to identify that this is an escape character that was added, and therefore it will be able to remove that from the data and not interpret that as a special character as such. So what is normally done? So in the case of character stuffing, that is in this case of byte stuffing, so what is normally done is that we have this extra DLE character which is added into the data stream just before the occurrence of the actual DLE which is there in the data stream. So as I said, on the receiving side, the data link layer will destuff this DLE. So destuffing in the sense that it removes this DLE before giving the data to the network layer. Because remember, this was something which was added only by the data link layer, so it's removed by the data link layer. So let's just take a look at how that is normally done. So let's say this is our actual data being sent. This is the actual data being sent. So we have data, your start of character, end of character, and so on. So now let's say, for instance, looking into the data, we find that there is a DLE character which is a special character which is being actually sent as part of the data. So what is done now? You have to stuff it. So what is the stuffing mechanism that is used? Whenever we see a DLE, you will add another DLE before it. You prefix it with another DLE. So this is the actual data now that will be sent with the stuffed DLE character inserted in between. Okay. So now at the receiving end, what will happen is this stuffed DLE character will be removed. So a destuffing will take place, and this will be your destuffed data that you get back. Remember, okay, you can see that this is the same as the data that was transmitted. Okay. So this is a simple byte stuffing mechanism that is used. Similarly, when we talk of bit oriented framing, we have the bit stuffing technique which is used. Now remember that the flag that we are using here is 0 followed by 6 ones followed by 0. Now this will correspond to the value 7e in hex. Okay. So that idea that is used here to do bit stuffing is that now we need to make sure that if this particular pattern occurs anywhere as part of the data, which is very much possible, you need to make sure that it does not get misinterpreted as a flag. So the idea that is used is that the moment you see 5 ones, you insert a 0 after the 5 ones. So the sender will always insert a 0 after 5 ones. So the moment it sees a series of 5 ones in the data, it just inserts a 0 after that. And what the receiver will do is, it will remove a 0 which appears after 5 ones. So automatically the stuffed bit which was inserted by the sender is removed by the receiver. So let's take an example of that as well. So let's see. So let's say this is the input stream that we have. You can see here that you have a series of ones over here. You can see that you can have a series of ones 5 ones here, there's a series of ones over here as well. Okay, so now what will be the stuffed stream for this? So that is, we said that after every 5 ones, 0 will be inserted. So look at this here, you have 1, 2, 3, 4, 5 ones here. So a 0 is inserted here, right? So after this, there are 2 ones. So those 2 ones come over here. Then you have a 0, 0. Now again, see that there are 5 ones here. So the moment the 5 ones are seen, a 0 again is inserted. So you can see there's an extra 0 that has come in here. Then this 0. And then again, there are a number of ones. So after every 5 ones, we have to insert a 0. So 1, 2, 3, 4, 5. So there's a 0 inserted. Another 5 ones. So another 0 inserted, and so on. So the algorithm used on the receiver side will be, the moment it sees 5 ones and sees a 0 after that, that 0 must be removed. So you can see what happens here. So at the receiver side, the moment it sees 5 ones, a 0 after that, so this 0 is dropped, right? And then you will have your 1, 1, 0, 0 coming in. So you can see that you got back your actual data. So same thing is done at the end for each of the stuffed bits. You'll see that 0 is dropped, this 0 will be dropped, and this 0 will be dropped to get back your original stream of data. So this is basically how bit stuffing works. So whenever the sender data link layer encounters 5 consecutive ones in the data stream, it automatically stuffs a 0 bit into the outgoing stream. Similarly, when the receiver sees 5 consecutive incoming ones followed by a 0 bit, it automatically destuffs the 0 bit before sending the data to the network layer. Okay. So this is basically how the bit stuffing scheme works. Another framing technique which is used is a counter-based framing technique. So here, instead of having a sentinel character to identify the beginning of a frame or the end of the frame, so what is done here is that a payload length field, that is, what is the number of bytes that is being carried in this frame, is added in the header. Now this is a very simple scheme, but the problem that you can have in this scheme is that this count field that we have could get corrupted. Now if this count field gets corrupted, it will cause the receiver to think that the frame is ending at a different place. So what do we do in this case? What is the solution for this? The solution is that this has to be handled by means of some error detection technique. So which means that there will be an error detection field which is there in your frame, and using this field you'll be able to identify that some error has occurred in this particular frame of data, and so you will discard that frame and wait for some synchronization or something that will be used to identify the next frame. So you will require some kind of synchronization between these frames that are being transmitted. Now remember that this errors occurring could happen even in the case of our bit-oriented framing, byte-oriented framing, character-oriented framing that we talked about earlier. So even in those cases, you will have to resort to some kind of a error detection mechanism to identify the errors. Now to look at an example for our count-based technique. So this is an example that we have here. So this is a frame which consists of 5 character, frame 1, 5 characters. So the first byte that we have here is 5, indicating that there are 5 characters in this frame. Next, again you have 5, indicates that there are 5 characters in this frame. Then you have 8 characters in the third frame, so you have a value of 8 here. Okay, so you have your 8 characters here, and then again 8 characters, and so on. So as we said, when you have an error, which you can see over here, so let's say this 5 that we had here was due to an error became a 7. So in that case, on the receiving side, the receiver would think that the data begins here and the end of the frame is here and not here as it is supposed to be. So what will happen now? So these two characters, this 8 and 0, which actually belong to the next frame, will be treated as if they belong to this frame. Okay, and this one here will now become a character count. So this will lead to a problem, and as I said, we need to have some error detection mechanisms to handle these kind of errors. Now there are other framing techniques which are called as clock-based framing techniques, which is used in sonnets. We will take a look at this in the next session. So to summarize, in this session, we've looked at the functions of the data link layer. We've then looked at framing. We've looked at asynchronous framing and synchronous framing. In synchronous framing, we've looked at sentinel-based framing, where we looked at byte and bit stuffing, and then we looked at count-based framing. So we are yet to look at the clock-based sonnet, which we will look at in the next session. Thank you.